We're talking today about unlocking the future of drug discovery, high quality protein crystallization in microgravity. What we'll be doing today is giving an overview of the crystallization with very specific details on the Kirara offering. We're going to start with Dr. Hilda Stenuit from Ice Cubes, who will be talking about the Ice Cubes offering.
Well, good afternoon, good evening, good morning, wherever you are. So my name is Hilde Steenuit. I'm a researcher from background. I'm an astrophysicist, so I'm used to looking at slightly different scales than proteins, but that's fine. And after my PhD, I started working with company Space Application Services in a number of different functions. Space Application Services has headquarters in Belgium and also a subsidiary in the US, and people working in different European countries in a wide range of space topics. And for quite some years, I have supported the European Space Agency in a function of ESA Mission Science Office, so coordinating the different science disciplines on the International Space Station. And now, since a couple of years, I am supporting our IceCube service, giving access to space for research and more applied activities. And from our subsidiary, there is Anna as well, from Aerospace Applications North America, and they provide IceCube service in the US. And she's also there to answer any questions in the chat if you would have any that either she or me can help with. So enough about me, about us. So the reason I get to talk to you here is that we provide this service of direct access to the International Space Station that we call ICE Cubes, or full, it stands for International Commercial Experiment Cubes service. And you see some pictures here of some of the cubes or modules that we fly on a regular basis to the ISS for very different types of research and technologies. And we provide this service globally. We work with the European Space Agency in Europe and with NASA and the ISS National Lab in the US, where we act as implementation partner. And one of the partnership collaborations we are very proud to support is that with the colleagues of the Japan Manned Space Systems Corporation, so JAMSS, from Japan, to fly and accommodate an incubator allowing for proteins and molecules crystallization in space. And you actually see a picture of that incubator cube developed by JAMSS on the left bottom picture, and Sato-san from JAMSS and Tanaka-san and from Confocal Science and Professor Suzuki will all be telling you more about the incubator, the protein crystallization incubator, and the applications they have been looking into. So I'm very grateful for the colleagues of Space Commerce Matters with Cindy and Jose who coordinated this webinar. And the message we typically pass is that crystals grown in space come out larger and better structured than the same ones on Earth, and they have less imperfections, which would help to reveal the structure and function of these proteins and molecules more clearly. And in fact, I put there on the right a reference and a summary table of a recent publication from the group of Dr. Ann Wilson from Butler University. And that group has done a retrospective analysis of public domain data of crystals that have been grown in microgravity. And that publication, in fact, the initial one and also the more recent one, support with figures, and you see a summary table of some of them on how much larger, how much structurally better and more uniform and so on the crystals in microgravity are compared to the same ones on Earth. So I think we will be hearing some very interesting presentations on the application fields that include drug discovery, but also go beyond drug discovery, more in the area of biotech and material science. And I'm very much looking forward myself to hear all of the presentations. And with that, I would like to hand it back to Cindy to introduce the next speaker.
Thank you, Hilda. And so now I would like to turn it over to Mr. Sato from JAMSS.
Thank you very much. I'm Naohiro Sato from Japan Manned Space Systems Corporation. First of all, I want to say thank you to Space Commerce Matters to give us these great opportunities. And I want to say thank you to my audience. It's my great pleasure to introduce JAMSS commercial service Kirara in space production using ISS here. And the Kirara service is provided with worldwide team in their commercializations. We have support from space application services. As Hilda mentioned, already introduced that we use the service of IceCube's facility in Columbus module. We also have partners who is confocal science, and Mr. Tanaka will present his results later. But they support crystallization preparation of the experiment using their crystallization tubes. JAMSS is the integrator of Kirara services. We have also developed our own cube. That is a very small one, a 10 centimeter cubic incubator, but it can contain several tubes inside and keep the temperature of the samples around 20 Celsius degree. Actually, as I mentioned, that the Kirara service is really provided with worldwide team. Kirara Cube is installed on IceCube facility as shown here. So small tubes with samples is located inside our incubators. And then our incubator is located in IceCube's facility in Columbus module. Target of Kirara services was that initial idea was that to facilitate drug discovery research through high quality protein crystallizations. We also still have several researchers and clients who use Kirara for drug discovery support, drug discovery research. But now our service is also expanded to beyond protein crystal growth to material synthesis in a microgravity experiment. In microgravity environment. So our cube is really small, but our clients can test their idea using our small cubes with relatively low cost. And if it works well, they can try to develop their own larger facilities on board if necessary. And because we provide the services, end-to-end services for clients, customers don't need to be specialists of the space missions. So they can just send samples to us, and we give them back the result from the space later. Kirara already accomplished 5 missions successfully. Our first demonstration was done in 2019. It was launched by SpaceX 19 in December. And in 2020, it was the time of COVID-19. So Kirara number 2 also has the samples of the first COVID-19 drug research in space. In 2021, that was the third mission of the Kirara. We also have some STEM program samples and label prepared by school students. And in 2023, we had two missions, Kirara number 4 in March and Kirara number 5 in November. In these missions, we have several new types of experiment, such as organic compound microcrystals and production of bacterial cellulose and colloidal crystallization. Some of them will be introduced later. As I mentioned, that the Kirara also provides some STEM program for school students. And this is, I think, this is a great opportunity for them because they can experience real space missions, not only just lecture. So actually, the sample itself was a lithotrium, very simple one, but some of students could get very good crystals from space. Next Kirara is planned in end of February 2025 at the earliest. So we are now calling for the samples for the Kirara. For more information, please visit at our website. Thank you very much, and I hope you enjoy the presentation from our Kirara users. Back to Cindy.
Thank you very much. Very interesting. And congratulations for so many successful missions so far. Very impressive. Okay, so let's turn it over to Confocal Sciences. And I think this presentation from Mr. Tanaka will be very interesting because I think the services that Confocal Sciences provide are really a differentiator in the crystallization work that's being done and the end-to-end services that are being provided. So again, Mr. Tanaka, thank you for being up so early, and over to you for your presentation.
So I'm Hiroaki Tanaka from Confocal Science, and I have been engaged especially in the protein crystallization in space for more than 30 years. And I had a lot of experience, especially from JAXA PCG project, developing method, developing devices, operational procedures, and also user integration, etc. Some of the results have been published, and you can find them from this website. And some devices we have developed can be purchased from our company. And now I am supporting JAMSS Kirara project from its beginning. Well, the essence of this Kirara service are already reported by Sato-san, but I must mention that the 96 samples can be installed inside of this very small cube, 10 centimeter cubic. So you must understand that all the samples are very small. The original sample mounting method in Kirara is the counter diffusion method for the protein crystallization. In this method, protein samples are loaded in the glass capillary, and the end of the glass capillary, a gel tube, a silicone tube with a preloaded agarose gel was attached. And the other end, we sealed with a sealing compound. And this assembly, capillary assembly, is dipped in the reservoir solution. And the reservoir solution then diffuse inside. If the concentration of the crystallization reagent increases, a protein crystal starts growing. But in the Kirara, the configuration of the experimental device is a little bit critical because it needs the double containment configuration. So we prepared the outer bag, and with the outer bag, two inner bag with the two cylindrical tube formed on the plastic tube is installed inside, and here the two capillary assembly are installed here, and so 4 capillaries are installed in the one sheet. One sheet means the 2 tubes, 2 crystallization conditions, and 2 capillaries each. And these bags are made from the non-gas permeable soft plastic sheet. That means it's soft and can be sealed by heat sealer. And the reaction is basic mechanism is mixing 2 solutions. One is in the inner vessel capillary, and the other one in the tube. And in usual, we can stop mixing, stop diffusion by clipping the silicone tube part by some mechanism. Well, this is easy method, for example, by double clip. And the bags, vessels, experimental method, and procedures can be customized for, especially for the other than the protein crystallization. Actually, samples are loaded in Japan and 2 or 4 weeks before launch. And so, therefore, it is necessary to suppress reaction before launch. So, the nominal method is to apply diffusion stopper, that is clipping the back from outside. This is the nominal diffusion stopping device for the transportation. And but for other than the protein crystallization sample, we can reduce the reaction by storing in 4 degrees or in ice, dry ice during the transportation. These are for especially the biological samples. And at the Kennedy Space Center, about 2 days before launch, the stopper will be removed and it will be transferred to room temperature. Then reaction starts. So this means that the user must consider the reaction starts 2 days prior to launch. So it is necessary to optimize the reaction beforehand, that the major part of the reaction should be performed in space. This is the rough timeline in the Kirara service. The user should submit the application data sheet about 4 months before the scheduled launch date. And 3 months before, samples for the optimization should be sent to us if user needs to optimize the crystallization or other reaction conditions. And about 3 weeks or earlier, all the samples should be sent to us. And we load around 2 to 4 weeks before the launch. Then the samples are transported to the case sheet, installed in the ice cube, launch, and after about 1 month of the launch, they are recovered from ISS and delivered to users. This is the list of the samples launched in Kirara about the protein crystallization, not only for X-ray diffraction crystals, but also the neutron diffraction and also the crystals for the STEAM education. But in addition to these, other kind of the samples such as colloidal crystallization, small molecular crystallization, and enzymatic cellulose synthesis and bacterial cellulose production has been launched. Well, the benefit of the protein microgravity on the protein crystallization is summarized in this slide. It is often observed that the cluster-like crystal growing on ground will give a good single crystal in space. That means that there is improvement on the shape of the crystal. But in addition to this, it is often observed that the maximum resolution is improved, mosaicity is reduced, R-free value is reduced, that means improved, and sometimes twin fractions observed in ground will be reduced in space. These statistics are obtained from the alpha amylase crystal grown in the Kirara first flight on 2019. And from these good data sets, you can see very clear electron density map like here, and a much accurate atomic coordinate has been obtained. And you can find that from this data set, the electron density map obtained from the space-grown crystal is very clear. This part is a 5 sugar molecule attached to that protein. It can be clearly seen here. But from the ground-grown crystal, only 2 sugar molecules can be observed. Other molecules cannot be seen like here. And so that means that the atomic coordinate cannot be assigned like this part. So these results give a good suggestion. If this part is a drug candidate compound attached to the target protein, you can find how it bound in clearly in space-grown crystal. And this clearness will be very helpful for the drug designing. Well, but today I go to the other result of the other materials. This one is the result of the enzymatic cellulose synthesis in Kirara first, launched in the 2019. In this experiment, CDP, that is the cellulose synthetic enzyme, and cerobiose, that is a primer of the synthesis, are loaded in the glass capillary. And alpha G1P, which is a substrate, is loaded in the tube. And this is the gel part, and we clipped during the transportation and released in KSC. After the sample recovery, it was found optically that something uniform material was observed inside the glass capillary. And with using the scanning electron microscope, very fine sparse networks was observed inside. This was from the ground-grown, ground synthesized cellulose, so the difference is very clear. And this enzymatic cellulose synthesis in space is the first time in the world. But we also launched the cellulose sample, another type, that is production by the bacteria. In this case, the bacterial culture was loaded in the gas permeable inner bag, in the non-gas permeable outer bag, and these two outer bags are coupled and stored in the outer bag. And the diffusion stopper were applied in this part to separate the culture and the air, and stored in 4 degrees for the transportation. At this situation, the culture are anaerobic and the temperature is low, so the bacteria is inactivated during the transportation. And at KSC, diffusion stopper was removed and temperature increased. Then they start producing the cellulose. And after 1 month, they are recovered, and we can find that the cellulose are synthesized, are produced in the culture bag. And this is also the first time in the world about the bacterial production in space. And we can find that the bacterial cellulose production is possible in space. And then we scaled up in the Kirara number 5 flight. This device is using double gas permeable culture bag. The culture samples are installed in the inner bag. Then 2 inner bags are installed in the gas permeable outer bag. And Then the samples were placed in the anaerobic back and stored in the 4-degree for the transportation. At Kennedy Space Center, the samples are picked out from the outer non-gas permeable back and increase the temperature to 20 degrees and then launched. The production date was adjusted beforehand so that the major part of the cellulose was produced in space. And as you see that the cellulose was successfully produced in space. This result suggests that the larger scale production is possible in space and in near future, maybe on Moon or on Mars. So, as is here, we can optimize containers, experimental method, procedures, and other things according to the user's request. But it takes certain times. So it is preferable to contact us as early as possible. And we are very much welcome your entry. Thank you for your attention.
Thank you very much, Mr. Tanaka. And I don't know about everybody else, but I definitely have some questions based on what you presented, especially given the reaction, begins 2 days before launch. And your optimization process, what does that look like? So let's hold on to that. Let's make sure we get through all of this material. So now we are going to shift and we are going to play a pre-recorded message from Mr. Suzuki from Tokushima University. And he's going to tell us a little bit about the work that he has done in colloidal chemistry in space using the process that both Mr. Sato and Mr. Tanaka have described for us.
Hello, my name is Yoshihisa Suzuki from Tokushima University in Japan. And today I want to talk about the colloidal crystallization under microgravity. And I want to talk about these contents. First, I would like to introduce my study and experimental results and discussion. And finally, I want to talk about conclusions. Okay, so probably many of you don't know about the colloidal crystals. Why do I study the colloidal crystals? Because this is a typical movie of crystallization of colloidal particles. And this is a movie taken by using the optical microscope. And these particles are the colloidal particles which have a submicron length scale. And there you can find a regular array of particles here. So by adding the depletant chemicals into the particle dispersion, we can induce the attractive force between the particles. The attractive force is a driving force for the making a colloidal crystal. And by observing in situ during the crystallization process, we can really find a very precise elementary process of crystallization here. This is the main reason why I do the colloidal crystallization. And of course, there are the many other very interesting properties of colloidal crystals, but today I want to focus on the first reason. Okay, so I want to introduce our studies so far. First, I successfully enlarged the colloidal crystal by using the centrifugal sedimentation. But in this case, colloidal crystal is formed with a repulsive force. But anyway, so you can find a uniform green colored object. This is a crystal, colloidal crystal. And if you measure the spectrum of the visible light length, and you can find a peak of the green color here. So this is from the crystal, and this is caused by the black diffraction of a colloidal crystal with a visible light length way. Okay, so this uniformity shows we could successfully enlarge the colloidal crystal. And the second one, shown you before, that we can easily observe the elementary process of crystallization simply by using the optical microscope. And recently, we also successfully measured the vibrational frequency of each particle on the top of a gross interface of a colloidal crystal by using the high-speed camera. Okay, based on our experiences, and today I want to talk about the purpose of a present study. And okay, so in this study, we tried to crystallize the silica and the polystyrene particles under microgravity because in many cases on the ground, on the Earth, we only could crystallize at the bottom of the container because such kind of submicron particles can very easily set down. And so we cannot make three-dimensionally large grains of a crystal. We can mainly obtain the two-dimensional or planar-shaped colloidal crystal. So I hope that if we can utilize the microgravity conditions, we can make nuclei at the middle of a solution, and we can enlarge the crystals in the middle of the solution by floating. And so that we can finally obtain such kind of three-dimensionally large and high-quality bulk colloidal crystal. So that was the purpose of our study. And so in this study, we used the both polystyrene and silica particles. And to induce the depletion attraction force between the particles, we add the aqueous solution of sodium polyacrylate like this. And we used Kirara system, and in the box, we put the samples like this. Here, there is polystyrene particles down part, and if we inject very gently the aqueous solution of sodium polyacrylate, we can keep the boundary like this. And so also this is a sample for the silica particles. And upper side, there are the sodium polyacrylate solution. So just before launch, I asked the ground staff to mix each other to induce the attractive force between the particles. Okay, so I want to move on to the results. And first, I want to show you the results of a silica colloidal crystal. And this is a movie which is taken during the intentionally change the focal plane by moving the focus. So first. Anyway, so we find round-shaped grains of a colloidal crystal, but it's by changing the focal plane, we can easily confirm the inside of each round-shaped grain. We could successfully make a very good quality colloidal crystals of silica particles. Okay, so in the case of the polystyrene particles, we could also successfully obtain the three-dimensional colloidal crystals. And also the inside of each grain, we could find the regular array of particles. And it's a little interesting because we can also find polygonal shaped grains to some extent. Then in this case, these grains are from the wall, I think. So but I'm not very sure about the precise reason why. Okay, so we also find that thread-like aggregations of particles like this which we have never found in the ground-based experiment. So this is also very interesting. So anyway, so we consider that we could successfully obtain three-dimensional crystals. But anyway, so we should return the samples from the space, and during the returning process, these colloidal crystals should settle down, and some quality of crystals were deteriorates to some extent during the returning process. Okay, so I want to conclude this work. And first, depletion-induced attractive force resulted in the three-dimensional crystallization of silicon polystyrene particles under microgravity conditions in the ISS. And almost all of them have three-dimensional shapes and high crystallinity, but the outer shape is rather round. Okay, so the in situ observation in the ISS or gelation of sample is indispensable for confirming if we could really obtain the three-dimensional colloidal crystals in the ISS. Okay, so right now in situ observation is very difficult because the box is very small. So in the future, at first, I'd like to try the UV light sensitive gelation of the colloidal crystal and sort and the colloidal crystal. We can fix by gelating the solution by irradiating the UV light. If we contain the UV light sensitive gelation agent inside the solution, we can fix the situation in the under microgravity conditions. Okay. This is a typical example for the gelation, the fixation of by using the UV light sensitive gelation agents. And to use this, we can fix the situation of the grown crystal like this. Okay, thank you very much for your kind attention.
I want to start with one question that came through, and Hilda, this one is for you. How accessible is this service? You know, we've been hearing a lot from our Japanese colleagues on this fantastic work, but how accessible is this service to Europeans, to US participants that are on this webinar and that will be watching this in the future? And could you just talk a little bit about that access?
Yeah, absolutely. It is fully accessible globally. So there is a great help both on JAMSS and confocal science side. And so when European scientists or American scientists or any other scientists are interested to participate to one of the Kirara missions, They can either contact us in Europe, they can contact the people that I was mentioning with Anna and Jessica, or yourself, Cindy, and your group, and we would put you in touch as a scientist with Sato-san and Tanaka-san, and they would help you through the whole process. As Sato-san was mentioning, there's no need for any of these scientists to know the insights of space processes, so that's exactly why we set it up, or why it has been set up the way it has been set up. So to make it accessible for anybody around the world with all of the expertise. And as Tanaka-san mentioned, that expertise goes back quite some decades. So yeah, it's accessible for anybody around the globe through these point of contacts, let's say.
Could we talk a little bit about the pricing? You know, how does that work? You know, we get questions on that. Is that on a case-by-case basis? Is it on a tube-by-tube basis? You know, maybe talk about.
Yeah, actually, I need to for the pricing thing that we need to talk with our sales office. But our service is sold by tube basis. So we always give the prices with one tube per tube. And for the one tube launch, it depends, but it's roughly a few K dollars per tube. Not 10K or 20K, but a few K tube per tube. And if, as Tanaka-san mentioned, if the samples need to be optimized for the launch, well, or some clients not sure about the crystallization on board, so sometimes we need to test on ground for further investigation. In that case, we need some additional cost for that. But for just launch the tube, if the sample is prepared well, that they can experience the space missions with a few K dollars per tube.
That sounds pretty reasonable. A few K is better than a lot of K. So very, very good. And so you just mentioned optimization, and that's what really caught my ear when Mr. Tanaka was talking, you know, about the reaction being or starting a couple of days before. Just a little bit more information, Mr. Tanaka, about the optimization that goes on before the launch.
Okay, so can I show the PowerPoint just now?
Sure.
In the case of the protein crystallization, the crystallization reagent is diffused inside the capillary, and the diffusion rate is not so fast. That means that if the crystallization reagent low molecular, for example, the salt are used for the crystallization reagent. In that case, it takes 2 or 3 weeks to become the equilibrium. If polyethylene glycol, for example, the molecular weight is more than several thousand, it takes 2 or 3 months. So most of the crystal will not start crystallization after 2 or 3 days. But sometimes very fast change may occur. Other case, we reduce the concentration of the crystallization reagent of the solution, or decrease the concentration of the protein sample. That is typical method for the optimization. But other case, for example, the enzymatic cellulose synthesis, we adjust the concentration of the CDP and cellulose and alpha G1P. There are 3 parameters, so it is a little bit difficult to adjust the condition. And in the case of the bacterial culture, the number of the bacterial cell is controlled, and also the concentration of the nutrition material of the culture also adjusted. So it is rather difficult, but we can perform them. Well, why we must do such a optimization is because we don't expect to have operation of the astronauts because of the reducing the cost. So if some mechanism, a low-cost mechanism may be added to the ice cube facility, the experimental procedure may be much simpler and much easier for the optimization.
All right, we have another question from Mario. Are there ways to scale any of the techniques we've talked about to production levels?
This is a great question because for the just protein crystallization, the small scale might be sufficient. But for example, as already Professor Suzuki mentioned, if they want to produce more colloidal crystals in steady conditions, that much bigger cube might be necessary. So as I mentioned, that the advantage of Kirara cube is that they can try their idea with a relatively low cost. And of course, from JAMSS perspective, if we found that okay, cellulose synthesis is great opportunities for the space productions, or colloidal crystallization is great opportunity for us, that we may develop the bigger cubes to produce for them. So as I said, that again, that Kirara is a really trial services for them to try their idea. And of course, if it works well, we can collaborate to prepare for the larger scale experimental apparatus.
I'm seeing that Richard Godwin, who is a iconic figure in space research and development, has asked a question. And Richard, I don't know if you want to ask yourself, but I will, as you're unmuting, what Richard is talking about is what's more important these days, resolution and therefore the size of the crystals grown, or the purity. So Richard, I don't know if you have anything to add to what you typed there.
Thanks, Cindy. Yeah, it was when I was looking at this in the past, the resolution capabilities of X-ray diffraction was coming down and down and down to the point where I only saw a small window for use of microgravity to be able to grow the size of crystals that were needed prior to that X-ray resolution. So it struck me that the purity of the crystals was more important these days than actually being able to identify the shape of the crystal. Is that a correct assertion?
I will reply about that. That the deterioration of the crystal, in my opinion, is very much dependent on the incorporation of the impurity molecule into the crystal. And under the microgravity condition, there is some mechanism of the rejection of the impurity incorporation into the crystal. So inside the crystal, the protein purity is improved, and molecules are arranged regularly. So the maximum resolution is improved, and also the mosaicity will be improved. That is actual thing, and I have studied theoretically, and numerical model have been developed, and they are published already, and you can find from my publication list. So please visit the ORCD website.
And Richard, great question. I know that we continue to talk about that, not just on, protein crystals and biopharma uses, but on the non-organic, the semiconductor, we have those fierce conversations on that exact topic. And so Yuri, nice to see you here, Yuri. Do you want to ask your question on the process itself? Yuri is asking where should the samples be, where should we send the samples to use these services? And Yuri, do you wanna comment or further expand on that?
Yeah, thank you so much for the presentation. I'm based in Japan, but I assume most of the attendees are based in US. So, should we send a sample to Japan from the US? Also, I wanted to ask who will own IP about the results gained by using your services.
Yeah, thank you very much for the question. That the all samples we need to gather once to the confocal science in Japan because of the filling to fill the samples to the tubes, and the samples will be shipped to Kennedy Space Center by JAMSS. So anyway, first of all, that all clients need to send the sample to Japan once. And as for the IP, we never call for the claim for the IP. So all IPs belong to the users. So we never request any right of the IPs.
Great. Yeah, I think one of the biggest focus areas of the work we've been doing on the International Space Station, whether it's a national lab or some of these other commercial services, is the intellectual property is the property of the of the researcher. We're really trying to open the doors of space-based research and manufacturing and commercialize the whole process. So Yuri, great question. We are now out of time. I can't believe how time has flown. I want to just thank again the presenters. Again, thanks everyone for your participation. You'll be getting this material from us after, and we really appreciate everyone's attendance and participation. Thank you.